Everyone, welcome to week 3. Obviously, this lecture is all of the week 3 content. In particular, it's class types. It should be a fun lecture because I don't think there's anything in here that's particularly hard. I think there's a nice range of stuff that you already know, which will give you some confidence, and it's really important for the second assignment. It doesn't really have a lot to do with the first assignment. The first assignment really had nothing much to do with object-oriented programming, besides the idea that, things in C++ are objects. You weren't actually doing much with creating your own object types, or classes as we refer to it. Now, Comp 6771 actually has remarkably little in the way of prerequisite requirements for the course. It pretty much just assumes that you've done like a data structures and algorithms course, and then it also assumes you've done an object-oriented course. So in this particular lecture, we're not going to really spend much time going over, what a public and private field is, or a public and private method, or the idea of inheritance, how one class can inherit another class, because we do assume that that knowledge is known at this point. So let's just kind of get into it. So why are we talking about classes? Object-oriented design principles are a huge part of programming, right? That's not to say they're, the be-all and end-all. Some people out there are big fans of functional programming, and then you've got, your C-style procedural programming. But object-oriented certainly has had quite a swing in terms of, I guess, its significance and relevance. Oops, clicked a big button. And relevance in what we're all doing, right? And what the hell did I do there? Jeez. 2 seconds. Yeah. So we're going to be talking about scope and namespaces and class types. So a lot of the stuff at the start of this lecture actually doesn't have a huge amount to do with classes. It's more about some of the precursors to thinking about classes, and also it kind of uncovers a few things we've been deferring up until this point. So firstly, scope. Scope is something that either you're going to be explicitly aware of it and know how to talk about it and explain it, or you are going to kind of intuitively get it even if you couldn't explain it exactly. So every time you declare a variable or function, this is kind of true for any language, but this is specific to C++ because there might be some nuances. That variable is valid in a particular scope. What that means is outside of the scope, if you use that name, because a variable has a name, the compiler is kind of like, I don't know what that is. And if you use it inside that scope, the compiler does know what it is. The scope rules are pretty straightforward. The scope starts at variable definition. So when you define the variable, everything under that indefinitely, so to speak, is, within scope. That variable's within scope. And scope usually ends at the very next brace. And what that means, and you've probably seen this before, right? If I've got a program here, int I equals 0, if I have an int main like this, think about it intuitively for a second. You know that if I try and printf, not that you can, but if I tried to printf I here in C, that doesn't work because it's like, what is I? Similarly, you might not have thought about this one as deeply, but if you have a function like this, and then you say, well, int j equals 0, j is less than 10, and j++, well, outside of this loop, if you tried to printf j here, it also wouldn't work, because thinking about those basic scoping rules, it is defined here inside that for loop, and it basically goes out of scope at the next curly brace. Now, that might be, again, if you take that too literally, it might be confusing, because you might think, well, I comes in scope here, but then it should go out of scope at the next end curly brace. But naturally, that doesn't really make sense. But basically, everything in C++ is usually scoped with braces of some sort. So this for loop is an open-close brace. This function is an open-close brace. And nearly everything we're doing is like if statements, else statements, for loops, while loops, and function definitions, and they're all just kind of braces. So, you have a block, and everything in that block that you declare is in scope till the end of that block, right? You could think about it a few different ways, and I'm sure there's some very nuanced rules that go really, really deep. But that's all just the abstract. What's important when it comes to scope is that we always want to define our variables as close to their first usage as possible. And what that means is, if you're going to do something inside of this loop, such as, printf j plus 1 or I plus whatever, int k equals I plus 1, you would like to print it here. You would like to define it there. You wouldn't want to go and define it on the line above. You'd want to define it in here. So you kind of want to get in the habit of defining variables as late as humanly possible. In general, again, just like the best practices guide, all this stuff we share with you is a good general rules. There's always going to be some exceptions. So, I'll see a forum post, someone's written like 10,000 words about, why this particular use case, the rule doesn't make sense. And that's okay. There's always exceptions, but in general, you want to define it pretty close to where it's used. That doesn't mean the line above. Sometimes it could mean 10 lines above or 50 lines above. It's more just like there's going to be a point 1, 2, 10, 50 lines where you can't really feasibly get it closer. And what you're trying to avoid is taking it even further away, because that's when things, are kind of bad. Now, naturally, this might conflict with some ideas that you get taught in, maybe first year, where, at the top of the function, you'll go and create all your variables like this. Again, coming back to what is good or not good, there's no universal rules with this. It's just that, when it comes to C++, we are typically writing it a little bit more like a higher level language these days. Whereas this kind of approach up here, where you define all your variables at the top of the function, is probably a little bit more C style in nature, and probably tied to the fact that you want to kind of have your, you want to be really clear what memory that function's taking up. Like, that's a great thing about the C style approach of where you declare stuff, is that it's all right there. And you can be like, yep, okay, 4 ints. I can kind of visualize how much that's going to take up on the stack. But again, that's a little bit, older style approach. Tim in the chat says, example in that code, have to declare I before it's first used to make sure it's valid out, make sure it's in scope for the return statement. Yeah, I don't know about I think I should be fine there. I think it's more J here. So like, one case that might come up is someone wants to return J from that function. This is a good example of where it doesn't work. In those cases, sometimes you might actually need to pull that out and put it here. You can do things a few different ways. You can do it like that, where you just have an empty element in that for loop. Some people might also go and do something like this, where they actually declare it on the top line and then, define it here. I know that these lecture slides say scope starts at variable definition. I guess it should be variable declaration. Or definition, because remember, all definitions are declarations. Again, the power of words here. I kind of said that. I said this a week or so ago around talking about languages, and I think this is a good example, because now that we know the difference between a declaration and a definition, which word we use on this slide, which I think we've used the wrong word here, can suddenly change your entire understanding of what something means, which can be tricky. Tim says, my point was just that your code is the example that breaks the rule of declaring as close to first use as possible, and it's necessary to give I the right scope. Yeah, it's a bit of a here and there example. We'll probably look at some better examples, so I won't spend too much time on that one. So if we have a look at this first piece of code here, scope.cpp. Now, I like this little example because it kind of gives you a really good sense of scope. And maybe we've talked about it enough now that you might be able to picture it. So if I look up my scope.cpp file, I want you to think really carefully about what output you think this program is going to print. Pause the video. I guess everyone's either live or watching the recording. Pause it and think about it, right? Because you can see that it's got 5... STDC out. So that means we're going to get 5 numbers, 1 on each line. And I'm just going to go and run it for you for the, impatient types here. Make scope. That should just build for me. And then 3.1 scope. Just giving it a sec. Cool. 1, 2, 3, 2, 1. Now, this is really interesting. And what I love about this is that when it comes to earlier year programming, you don't actually spend a lot of time thinking about the fact that the language can be aware of the same variable name in multiple scopes, because we kind of have this somewhat naive idea that we're taught, which is there's a variable called I, and then that there's only an I at a given time generally, and part of that's also because it can be bad style to reuse the same name. But you can see in this case, I've got a globally scoped I here. And what that means is that from now on, for the rest of this program, for 100 lines down here, if I use I, it's going to give me 1. However, when I enter this new scope, which is defined by the braces inside a function here, I print it, it's still going to be 1 because right at this point, the only I that's in scope is this one. But when I enter this if statement, I'm now inside another scope where I can redefine I, or I can define, and my point here is that the two I's exist at the same time, because when you standard C out this and you standard C out this, you'll get different results, because depending on the scope that I is, invoked or called, you are going to get a different output. You can also see here with these braces, this is basically, I don't know what the technical word for it is off the top of my head, but it's like an anonymous scope. It looks a little bit weird, right? Like it looks like it should have an if or an else in front of it, or a for loop or something. But this is valid C++. You can just go and define a scope straight like that, and create a little mini scope in here where that will work totally fine. So that's kind of scoping rules in a nutshell. So yeah, ways we can create scopes. We can create scopes with classes, which we're going to talk about today, which is kind of what this precursor is. Namespaces, which we'll also touch on, which is mostly just to catch up. Functions and globals you kind of get, and random braces are new. Probably won't use them too much, but it helps. So I mean, already, Ayush, I hope I pronounced your name right. What is usage of anonymous scope? Again, not really something super practical. I don't want to kind of be like it's super, super useful. I haven't had to use it too much. I've seen some code with it before, but it does just help you break out a scope, so maybe you'd like to redefine a variable with the same name or something like that. But again, I don't have any practical anecdotes for you, but it is important to understand that's how the language works, because it can exist if you need it to. Bill says, I think a good way of explaining this is that the higher scope shadows the lower scope for its lifetime. Yeah, I think that's pretty important, because at this stage in the code here on line 5, there's only one I, whereas once we get to line 8, there's now 2 I's, and once we get to line 11 or 12 here, there's 3 I's. They all exist at the same time, and they have basically a sense of hierarchy depending on, which is the deepest scope. Tim says, if you comment out line 11, will line 12 print 1 or 2? Surely 2, as per other languages. I believe it is 2. So if I comment at this line, it should, in theory, because there's no I in this scope, it should go up a scope into this one and look for an I, and we should get a 2, but we can really quickly run that and see. Yep, 1, 2, 2, 2, 1. I'll make that terminal a little bit bigger. So yeah, it behaves as we'd expect. So they're the different kind of ways we can work with scope. Okay, moving on to object lifetimes. Oops, sorry. Are they the same I mean the addresses. No, they're different I's. This is kind of the tricky thing I was referring to, is that with a piece of code like this, there are going to be 3 different, like the way to think about it is like they're 3 different variables, like you call them I1, I2, I3 in the back end, or however you want to think about it, but it's still just, referenced in code as I, but they are 3 distinct variables with different places in memory. And it's the compiler that uses the scoping rules to understand which particular one to reference when it has those, naming overlaps. Now, I don't exactly know, I think it's here. There's a line in these slides I wrote a while ago that summarizes it. So I'll just wait to see if we get to it. So, yep, that's the end of scope. Object lifetimes. An object is, okay, now we're just getting into a little bit of theory here. Lifetime relates to scope. Lifetime simply describes the period in which a variable name is valid, right? Which is another way of saying, what is the period in which the variable's in scope. So an object is a piece of memory of a specific type that holds some data. When we say an object, we mean something like a standard string or an integer or anything, right? All variables are objects. So if you're a C programmer, you'll just think of, variables refer to pieces of memory with a specific type. Oh my God. Microsoft Teams is force opening itself on my computer. I'm not interested. Yeah, and one of the cool things is that, C++ is generally a lot quicker to do this than other languages. Object lifetime starts when it comes in scope. That makes sense. We also know from object-oriented programming that all objects created of a class type, such as a vector or a string, because nearly everything's an object, in C++, they have, it has to construct the object. And we also know that each type has one or more constructors that says how to construct it. So if you define a class in C++, it can have a constructor, 2 constructors, 3 constructors, 4 constructors, etc. And they can have different parameters. It's a little bit like function overloading. And naturally the object's lifetime ends when it goes out of scope. As in when, like back in the previous code example, this int i3 here, its lifetime starts on line 11 and it kind of ends on line 13. And this I equals 2 starts on line 8 and its lifetime ends on line equals 15. And what we're also saying here is that every time an object goes out of scope, its lifetime ends, and therefore you have to destruct the object. So this particular example might be a little bit harder to understand, but let's just say for a second I replace those i's with, standard strings s, right? And instead of 1, 2, 3, I said like A, B, C. Now glossing over, a few specific details that, could make this example a bit silly. The point is that, you need to get into the headspace of whether it's an int or a double or a float or a vector or a string. They are all objects of some sort. So imagine everything is an object with a constructor and a destructor method that has to get called. So when you do something like this, the string's constructor gets called. And when you get to this line down here, the string's destructor gets called. You should know what constructors and destructors are by this point. Yep. Now, naturally, there's always going to be, when it comes to primitive types like an int, there's not going to be some super explicit, complicated constructor or destructor called. It just follows that primitive type behavior where it just allocates memory on the stack. But again, it's worth thinking about because when you get to things like, say, a string or a vector, when you construct or destruct a string or a vector, because they keep track of their own size internally, that means that at some point during construction, it is going to have to create another item on the stack or do another operation that will actually therefore track the size. So that is quite relevant as well. Did I skip namespaces? Am I crazy? Or is that later? I think I just thought it was sooner. All right, so we've been talking a lot about construction and destruction, right? So construction describes the process of allocating the memory and setting up for the creation of an object. An object is an instance of a class, or an instantiation of a class, and what happens if we have a piece of code like this where we say, hey, auto v1 equals standard vector int 1 and 2, we can see what that does. We can go to the CPP docs if we'd like to, and we can have a look at all the different kinds of constructors, because there are many kinds of constructors, and we can see that there is one that should take in 2 numbers that look like ints. It's not the first one or the second one. This one is probably the one it's going to do by the looks of things. Explicit and okay, we'll get to that later. Don't worry about the explicit part just yet. We will cover that later, but let's say for now, this one matches it. And what this says is that the first argument it takes in is a size. So in this case, the size is 1. And the second element is the value. So basically, I want you to create a vector with one instance of the number 2, and the type of this number 2 must match the generic type here, somewhat, intuitively. That's just one particular way to construct, and when that happens, well, what's going to go on behind the scenes is that the vector class is going to have a constructor somewhere that is going to go and malloc the memory to store that number 2, and then it's going to, create another piece of memory to store the size of the array as well. The underlying array, naturally. Construction can vary quite a bit. There's a lot to unpack here. We could talk about it for hours. So let's just talk about a bunch of little different things. Firstly, when it comes to constructing a vector, there are a bunch of different ways that we can construct a vector. And I think that's well demonstrated by what you see here as well. Firstly, you'll see that we could construct a empty vector, a vector with, simply call standard vector int v11 like this. Now, the always use auto way of doing this would be naturally to say v11 as standard vector int, empty brackets like that. That's this top one here. That's what that one is, and you can see there it's type 1, and it tells us here default constructor constructs an empty container with a default constructed allocator, right? The allocator part again is kind of, an unnecessary complexity here, but it creates a vector of type ints with no elements in it. Maybe it doesn't. It probably, I don't even think it would do a. Would it do a malloc? I'm not sure. It's probably said somewhere in the docs. Maybe there's a minimum size. I have no idea. But that's the kind of zero argument constructor. This is kind of where things get slightly weird though, and we will unpack this a little bit more. These next line here, which is the always use auto ones, what you'll see is that there is no difference between this braces approach and this parentheses approach. They both construct zero argument constructors, but the two brackets or parentheses don't strictly always mean the same thing. But again, we will come back to that. Here, what I'm doing is I'm creating a vector based on the begin end iterators of v11, or the default zero argument constructor there. So what that does is that kind of gets the start and the end iterator of that first vector we made, passes it into this new vector being created, which will then call the constructor here, number 5, right? Input iterator first, input iterator last, and it will essentially go through those elements one by one and copy them in. Now, naturally, in this case, it's an empty vector, so it's not really going to copy anything in, but that's what it would do. And then this one here, this creates a copy of v2, the one we just had, and makes it v3, which matches this one here. So this is when you create a vector and you pass in another vector and it uses that to copy it. And again, down here, you'll see that it's called a copy constructor. It constructs the container with a copy of the elements in the same type. Now, what I do want to point out here is that because at this point, v2 and v3 go out of scope, the destructors on v2 and v3 are called. So somewhere here, maybe where's the destructor? I'm trying to remember. Destructor, vector, destructor, CPP reference. Maybe it's, oh yeah, okay, I went up. I was too deep. That's right. Sorry, of course. So it's actually calls this particular function here. Now this syntax we'll see more and more, but generally when it comes to a class definition, and we'll see this in classes, the destructor looks like a constructor. It's just got a tilde out the front of it. In this case, it just says destructs the vector and all the used stories deallocated. So essentially, it frees all the memory at malloc. Fairly straightforward idea there. But the point is that the freeing or the destructing, I guess, of v2 and v3 happens on line 17. So you can't call v2 and v3 here because their object lifetime was only whilst they were in scope, which was there, whereas v41 and v42 and v12 and v13 and v11, they all get destructed here because that's where their lifetime ends, right? They all started at different points because they got defined at different points throughout the code. Now back to the braces parentheses problem down here, v41 and v42 use those two different methods of constructing. And it is a little bit confusing, but basically, and there's some slides that elaborate on this, so I won't ramble too much. When you create some types, like vectors, when you use the braces, what it will try and do with that is that it will try to create an object that just passes those elements in. Basically a vector with a 5 and a 2. And if you wanted to, create it with more, you could, 1, 3, 6, 7, like that. You could just go and add more and more to the end if you'd like to. This is called an initializer list constructor. And again, I do think we unpack it slightly. And you'll see it's this one down here, number 10. It's not immediately obvious, I find. But basically, it's a little nugget of C++ that lets you take a bunch of elements from a type, like a random array. Think of it like a Python style list, and just kind of dump them in and construct the object that way. Whereas when you use parentheses, it's going to look for a particular constructor that has functions that match that parameter list, right? And if I'm not making myself clear, another way to think about it is that in this case here, this looks for a constructor that takes in an int and then another int, whereas in this case here, it's looking for a constructor that takes one argument, which is a list of ints, or that standard initializer list that you'll see here. And the point of this slide is to show there's lots of different ways that we can construct things. So I kind of referenced this here. So we generally use the the parentheses when we want to invoke particular functions. Let me see. Yeah, we don't mention too much there. However, what we try and teach you in the course, which again largely kind of came from Chris at Google and stuff, is that we try and by default use the braces unless we specifically want to invoke a particular function, right? And what I mean by that is if you're default constructing an int, or your default or another int here, you should just use the braces as the kind of empty list. I couldn't tell you off the top of my head exactly why that view was so passionate, but I will rain check you on that and come back to you. But here, at least, you'll see that's how we like to do it. So we reserve the function calling for cases where we actually need to be like, oh, I need to call this particular function here and not some other function. So here you'll see you've got, here this is what it looks like to construct an int, a default constructed int, which will contain value 0. This one here is with the always use auto best practice. This one here is creating an int with value 5. Kind of goes on and on and on. Here as well, it's a bunch of extra code. Yeah, I mean, I think this stuff's a little confusing, but at least I used to find it quite confusing, so I can kind of empathize when other people find it confusing. But again, I just want to recap. Braces for everything unless you're like, I need to invoke a particular function here. So braces when you're kind of making a 5 like this or something else. Now, I don't think we enforce in the course that you need to use braces and construct an int like this. It's fine to do, auto I equals int or, 5 or something like that. There's no real issue with this. This code sometimes could get to the point where it's like nearly, again, confusing. But it is all possible. And the thing is, like, the reason we kind of talk about everything in C++ as an object is because in this particular case here, int's treated as an object. Like, even the primitive type int in C++ has a notion of what it's like to be default constructed. So doing this kind of calls the default constructor of int, which is naturally going to be something that literally just sets the value to be 0. Okay, now, why do we care about object lifetimes beyond some, academic, stretching, I guess you'd say? Can you think of a thing where you always have to remember to do something when you're done? Yes, you can. So, if we look at a piece of code here, like lifetime.cpp, what happens in this is we've got a void function called read words. It takes in a string, just a file name. And what it does is it creates an input file stream called f, where you give it that file name, creates a vector of strings called words, and then it uses some, STL magic. It uses the STL algorithm copy to, where what you do is you give an iterator to the input file stream there, and you give it a back inserter so that it inserts it into the words array. This is the kind of code that like I understand, but like truthfully, when I first saw stuff like this, I was like, this looks like gibberish. I don't really know what this is saying. But what I would do is if you find a line of code like that kind of confusing, all you have to do is simply go and sit down with it and make sense of it, right? Like back inserter gives you an iterator to the final element of the words array. And here copy, this gives you an iterator to the beginning of the file stream. And all it's going to do is go through every element of that file stream and copy it into the words array, right? That's very good use of STL algorithms there. And if we go back to the slides, what happens if we omit the f.close here? Yeah, what will happen? It looks a little like my v4 read lexicon. That's good. I like that, Tim. Good comment. So if we omit the f.close here, well, what's going to happen is we're not going to close the file, right? At least that's my understanding. And that can be tricky because, you imagine you have a program where you're opening many, many files and you forget to close it. Well, then you've got all your little file pointers of what's going on in memory, and, that could slow down disk, or God knows what could go wrong depending on the particular language and the particular use case. So it's important that you put that f.close there, but then you think, God, there must be an easier way than relying on programmers to have to call f.close to close the file connection. I don't think I seem to have elaborated on that. But a way around this, is that we can use object lifetimes to our advantage. And we'll see more of this come up when we talk about smart pointers in, I think, week 5. Can't remember off the top of my head. I think it's week 5. Is that what you do is you actually say, well, you know what? When f goes out of scope, I'm going to put all of the cleanup logic inside its destructor. And this is kind of where your brain, that is probably programmed to think a little bit in C, needs to think you have the benefit of an object-oriented programming language now, where if you want something to kind of always happen to clean it up, you can just go and define it in the destructor, which again, we'll talk about actually writing these classes later. But you could put something like that in the destructor, and then if it goes out of scope, great, all the file gets closed. The smart pointers topic we look at in the future is of a similar concept. It's a way of dealing with C-style pointers where we basically use the fact that there's something that monitors a pointer, and when that something that monitors a pointer goes out of scope, it gets rid of it. And what this comes down to, again, I'm trying not to ramble too much about future week stuff, is that everything on the stack is managed. The lifetimes are managed. Whereas everything in the heap that you malloc is just kind of there forever until you free it, till the end of the process, really. So this is us really taking advantage of the fact that everything on the stack will automatically destruct based on object lifetime rules, which are based on scope, when something's in scope or out of scope. All right, namespaces came up a little later than I expected it to. I think I must have moved a few things around. Namespaces are just another way to manage scope. They're not really more complicated than that. If you think about scoping rules like we saw back in that scope.cpp, all the different scopes allowed us to do was to reuse the same names again, if you think about it, and to use string S and string S in different contexts without having to call them S1, S2, and S3. And in a way, namespaces kind of are very similar. You think about really generic terms like std array or, std copy, think about all those STL algorithms and containers and everything else you see. If there was no namespace around it, then anytime you were to hash include it, you would just have these functions coming into your code. I don't know what the copy one is, but you just have these functions coming into your code like this. And if you had your own definition of copy somewhere else, then the compiler is just going to kind of crap its pants and be like, you've double defined this. Or even worse, not just that the compiler won't deal with it, programmers get confused about it because they're like, which copy is that? So the way we get around that is we use namespaces. So when we have a function like, our lexicon, what have we got here? You put a namespace around it like this so that when we invoke it later, we say lexicon, read lexicon. And that's what those double colons are. They're basically a way just to namespace something. Now, that syntax shouldn't be too unfamiliar to you because, again, many of you have done object-oriented programming where you know that if you have a class or a static type, you might have something like, booking system dot rooms, or dot rooms from Java or something like that, right? Where this is a class. So you are kind of already aware of the idea of using namespaces in a sense. It's just you've been doing the equivalent with classes or, whether it's the object or something else. It's just a way of, specifying and saying, no, this is this particular thing's version of read lexicon is what's going on here. So that's how we do it there. And then whenever we invoke it later, we invoke it like this or like this lexicon there. And what you'll see is that there's the kind of best practice of how to do this is people generally won't indent their code inside a namespace. I couldn't tell you why confidently, but I imagine it's just because namespaces are super ubiquitous in programming and they're typically the whole file. So it makes no sense to basically indent everything in the file just because it's in the file. So they kind of do it like that. And you'll also see at the end of the namespace, there'll typically be a comment with the name of the namespace, just so some, casual programmers can read it and make sense of that. Yeah, there's another example. There's the word ladder example from the assignment. Magic has said, do we allow to use anonymous namespaces in assignment 1? Yes, they're fine. I think there was some confusion around the best practices guide. We used to not have a best practices guide. It used to kind of be like word of mouth, which wasn't too great. So I put one together for this term, but there was naturally a couple of chinks in it. We've tried to clean those up. We've got an updated version coming at the end of assignment 1 just to avoid confusion. So look out for that with some extra examples and stuff. So we're always trying to improve those things for you. But yeah, you can use anonymous namespaces in assignment 1. That's totally fine. If you're not sure what anonymous namespaces are, don't stress. We're not really going to cover it right now, but you can always Google it, or it's not something you desperately need to do, anyway. But again, just talk to your tutor, help sessions forum, lots of information out there. Namespaces, I'm looking at this. Namespaces work for function declarations, function definitions, all kind of the same. And you can nest namespaces as well. The ways you can nest them are you can either nest them by, doing this where you have like a namespace 6771 and then inside of that you have another namespace called word ladder, or alternatively you could nest them like this if you wanted to as well. So if you wanted to say have word ladder 1 and word ladder 2 namespaces within a comp 6771 namespace, then you can do something like that. Though again, that's a little bit academic for me because I don't think I've ever worked on a piece of code big enough that really needs 2 namespaces, but it would still be out there. Okay, we'll talk about it. Okay. Sorry, I thought we might skip it, but I guess I included it anyway. So what you can do as well is you can create these anonymous namespaces, or anonymous namespaces? Is that what it's called? Yeah. What's the point of these? So we had this list earlier where you saw that we had class scope, namespace scope, function scope, global scope, random brace scope. One thing we don't have that you could argue that Python kind of has is file scope, right? So if you think about a language like Python, what happens if you have a Python code and you say I equals 0, print I, print I. If you import, imagine this is file 1. If you in file 2, call it file1.py, if you say import f1, is this how file 1? I think that's, I've forgotten how to write Python. If you do something like that, then naturally you can't access I, by default in a language like Python, all the stuff, and I think this is true for Node.js too, right? For those who've done JavaScript, all the stuff in that file is local to that file. But because of the way compilation works with GCC and those C-like languages, is when you hash include file 1 or whatever equivalent it is, when you hash include it and there's the linking stages during, after the code's compiled, all of that code is literally kind of copied and pasted in. So if you have code in, file 1, it's immediately actually global in everything else now too. And that's not ideal because it does just mean that if you're just casually writing your assignment 1 and you just go and create a function down here, helper function, then every other file that this gets compiled with, catch2, God knows what else, this will be in, well, depends on how the includes are done, but this can be in scope. So, in C, sometimes we talk about things like static. Static is a way to keep that file, that function or variable just within that file. But the way to do it in C++ is you create what's called an anonymous namespace, which is basically just a namespace with no name. Think of it like a little cheat code that if you do that, it's the equivalent of static and it keeps it within that file. So that's basically what an anonymous namespace is in this particular context. Here we call them unnamed namespaces. It does the same thing as static. So, you know, because we didn't like teach this strictly before, like, you know, I generally don't like having things on a Wednesday lecture and then you know, it's in assignment 1, so everyone's panicking for 48 hours to integrate it. So it's something that I'm going to tell the tutors not to like mark anyone down on, so don't stress for assignment 1, but it would be required for future assignments. So just think about that as well. Now, last thing on namespaces, well, actually not the last thing, there's a couple things. Namespace aliases also exist. So if you find you have a particularly long namespace, you can use that. This is, again, more academic, not something I'd recommend that you do anything with for your assignments, because for files that small, using a namespace alias is just kind of overkill. I mean, you can, nothing's wrong with it, just to be clear, like you're not going to lose marks for it, I can't imagine. But, you know, it's really useful for larger programs where you might have like larger software repos where you have, you know, 3 nested namespaces or something like that. Nam says, what's the difference between namespaces and classes? Well, a namespace is literally just a way to name a scope, whereas a class is, you know, a class with constructors, destructors, fields, and methods and all of that. Magic says, maybe the difference is the things inside namespace cannot become an object. Oh, you've answered that question. Tim says, do namespace aliases have scope? That's a very deep question, Tim. I don't know. Don't know. It's a good question. I'm not sure. Can Google it. Figure it out next week. Yeah, I guess that's true. Yeah, Tim's asking a really great question, which is like, if you go and just randomly put here namespace s equals std or something, right? Because that's the std, you know, namespace. That just means that here you could go like s.cout. You know, if you then come down here and do s.cout, will that work? I don't know. There's only really going to be 2 answers, I imagine, which is either no, that won't work and scope rules apply, or you can only define, I mean, maybe based on the editor, that's kind of telling me, but you can only define namespaces at the root level too. That might be the other answer. I don't know. I could try it out, but I'll probably just screw around I mean, I've already written the code. Let's just do it. Make scope. Ooh. Use of undeclared identifier I. Let me go and change these back to okay. Damn it. I'm just going to undo all that code. Give me a sec. Let's just get it back to where it was so we know we've got something that works. All right. Namespace s equals std, and then we'll just change that to be scout. I actually should probably put that inside here just so we can check that it works. Oh, I think I've done that right. Let's see. Yep, undeclared identifier s. Okay, namespaces follow scope rules. There you go. See, I hope that at the very least I inspire you all to remember that nothing stops you figuring that out, because I didn't know the answer and I can easily figure it out just by playing around with it. So all of you can too in the future. Very interesting. It's interesting that I actually thought it would go the other way, because I was kind of suspect on how the editor didn't like the namespace. Because there are some languages where there's just some things you have to define globally. Some of you might have come across some of those. Last thing is that it's important that we fully qualify our namespaces. One thing that many students who take this course always see in code examples, and they always ask about it every term, is they will see this piece of code here. Using namespace std. Now, I don't think it's even in the slides here. I'm not sure why. Sometimes when we were writing these slides, other lecturers had a view that if we don't talk about it, then people won't do it. It's true sometimes and true not. But this code is around the internet a lot. Lots of people like to do it. It makes sense because then you can just drop this thing here. It's not outright bad, right? Like I don't want to pretend, get all dogmatic and say, oh, it's the end of the world or anything like that. But what it is important to note with this is that it's doing what I would refer to as polluting the namespace with other information. What it does is it basically says, hey, you're in the global namespace here. You're in the global scope. So we're going to pull everything from STD, all the names that exist behind the namespace STD, and we're going to put them in the global scope. And what that means is you've got a global scope, and now there's a whole bunch more stuff in it. And it's really hard to kind of then track the code, because this could be a 1,000-line piece of code, and at the very bottom is a reference to something that is in STD, but it's not obvious because you use the namespace, whatever. Like you just have to be, like, yep. I need to do this, because otherwise it just might cause you more harm than good. And it's usually a bad idea to go and try and save like no one needs that amount of lines of code saved. I can't imagine why you need to do that. The time that might motivate you is if, for instance, you notice that your namespace is really long. It's got like 3 parts to qualify it. But then just go use a namespace alias, because then that's just a way to shorten the text in the program without, it's the equivalent of doing what we did before, right? With like namespace s equals std. Go and do something like that if you really need to. But again, you'd probably still need a good reason to do that, because it might confuse someone. But I would avoid the using namespace std part. I think it might even be in the best practices guide too. All right. Oh, last question. If you are in a nested namespace, should you fully qualify back to the root namespace? No, you don't have to do that. Everything within a namespace is totally fine. So what that means is if you're in here, if you're going to call word ladder here, you don't need to invoke it with like this something word ladder. Like everything inside the namespace doesn't need to be fully qualified. It's all the stuff outside the namespace. So object-oriented programming. Getting onto the classes stuff, just because it's late, we're just going to power through things tonight. We're not going to kind of wait around. Okay, a class uses data abstraction, encapsulation, interface, and implementation. I don't think there's anything we really need to cover there. All right, since you've completed 2511 or equivalent if you're a postgrad, C++ classes should be pretty straightforward. Classes define a new type. It's created using keywords class or struct. That's a bit of a funny thing in C++. It has either some fields or some member functions or some methods, whatever you call it. It's got private, public, protected, blah, 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 lots of different things. But me talking about that abstractly is not going to help. So, quick recap too. C++ follows other similar languages with public, protected, and private. Private are things that can only be accessed within the scope, the class scope. Public are things that can be accessed outside of the class scope by referencing foo.something, of that object. And protected is basically private, except can also be accessed by the inherited, elements. Now, that should all be recap. If you don't know what I mean, you probably should just go review that in your own time from the previous course you've done. But what is, I guess, maybe slightly different to other languages potentially, is that in C++ you can actually define multiple sections of the same name. So you can actually go public, protected, private, public if you want to. Now, I'm not saying that you should. That's probably very confusing for someone. It's more just saying that you can, and something to keep an eye out for. These things are important because you might expect the compiler to complain about something, and therefore if you think the compiler is protecting you, you might not be vigilant for it. So just remember that you can define that multiple times. Now, in terms of constructors, now we're getting into some actual, let's, write some code. Here I'm creating a class, right? This is the class, lines 3 to 16. Constructors behave very similar to other programming languages. That class I have, I create a public section and a private section. Note how the indentation is working as well. It's a little funny like namespaces where all of the class definitions, are indented in, but the actual public and private is in line with where the class is defined as well. Again, it looks a little bit silly, but that's pretty standard. What you'll notice with constructors is they behave very similar to other languages in the sense that the constructor's name is the same as the class name itself. So in this case, I have a class called myClass, which has a constructor, can tell because it's got the same name, that takes in an int I, right? Takes in just a single integer. And then what it does is it sets a private field contained within the class called I underscore to be that I, so that now after the constructor finishes, the value that was passed in is stored forever in this private field called I underscore. This is also a, style of the course is that private fields and private methods are suffixed with an underscore as well. So if you create private fields, you put an I underscore at the end. You'll also see that we can create methods here. This is all public methods called getVal. And you can just return the I as well. You can do that without any this qualifier or anything like that because this variable is in the class scope. So as long as you're within the class, you can reference it and the compiler will understand what it is. The reason we say the scoping rules are general rules is because previously we were like, well, something is in scope from when it's defined to the end of the brace. Now that doesn't really work here, because it's defined, well, it's not really defined there, but it's declared down here, then the brace is there, but it's actually in scope here. So there are subtleties to that kind of general rule, such as with classes, it's not that simple because with classes, it goes and has a look at all of the members of that class before it starts trying to make sense of the definitions and things of the constructors or something similar. Now, when it comes to creating an object of that class, because that's the terminology, because remember, my class is a class is a template. But here I'm creating an object of that type because I could have 100 myClass objects of the myClass class type because the type of an object is the class. This is just me saying auto MC equals myClass, and then I'm giving it these little initializer lists here. Now, I'm using the braces again because we always use the braces by default unless we specifically need to use the parentheses to avoid any miscommunication. In this case here, what happens is if my class doesn't have an initialized list definition, which it doesn't because it's our dinky little class, it will simply go and default to parentheses. So the braces, if it can't find an initializer list, will go back to parentheses anyway. So it's pretty common that we do that. And then we can standard C out mc.getVal. It'll call that public method, which will return I. And if we play with that code, constructor basic, we should naturally print out the number one, constructor basic. Constructor basic. 1. I get 1. Yay, super easy. So that's a constructor. The constructor initializer list that we talked about before. Oh, this is actually something slightly different. Sorry, I got my words mixed up. So there's this other part of a constructor called the initializer list. Let me jump to a code example to start. It's a funny little thing. So in C++, when you define a constructor, after the title here, the myClass int I, you can actually go and put this little colon here, and then what you can do is you can basically give it a series of, hey, here's my private member field, and then here's the value from the parameter list I want you to input to it. If you're not sure what I mean, let me go and create some more variables for you. So let's imagine that we have an I, J, and a K in this example. Int I, int J, int K. I actually will go and do something like this, where I say, yep, hey, when this function is called, what you are going to do is you are going to set I underscore to be I, J underscore to be J, K underscore to be K, and then you are going to call the function body here and print constructed. And getVal in this case will only, return I. We'll just keep that really simple. But if I try this out, oop, did that wrong. 10 points for whoever spotted that. What have I done? Oh, it's not used. Got to void these things out. Bottom of the terminal's just out of view. Oh no. Yeah, thank you. It's MacBooks and their stupid screen sizes. It's really annoying. You know, MacBooks aren't 19 by, was it 16 by 9? It's puzzling. I don't know why they do that. Makes me sad. 3.1, constructor init. Same thing. Constructed 5. Now, that's good. It means that we printed that out and we got the value 5, which was this first one here. This is an initializer list for a constructor. It's called a constructor initializer list. This is simply another way of doing this here. If I said I equals I, j equals j, k equals that. So these two pieces of code are conceptually identical, right? Because that's what you normally do, right? You want to set the variable so you go 1, 2, 3 like this. Now, why do we do that? Why do we... Yeah, I mean, maybe you can infer it from the slides and someone's got a good answer, but why do we like this initializer list? Just give people a second to answer on the chat. Oh, it's past my bedtime. Not quite, but... Give you a few more seconds and we'll keep going. Well, it's probably a silly question because I guess it's pretty well described. Well, what's described on the slides is it basically says when you construct an object of a class type, what it does is it goes and runs that, so it copies those in. And then what it does is it goes and constructs any of these that weren't copied in from the constructor initializer list, and then it executes the body. Now, a really maybe simple example of why that's important and why we care about this initializer list is because let's imagine for a second that I approach this slightly differently. My thing actually took in a standard string, and I didn't have the initializer list. And what I said was that s equals s here, like this. You know, so, okay, it's a similar class. It just takes in a string now, and that string might be like auto, string equals standard string. Hayden sucks a pineapple head. That made no sense. So auto MC, my class string, perfect. Yep. So here's the issue. What happens now is when we step through it, the constructor initializer list gets called and there is none. So nothing gets copied in. Then what happens is these all get default constructed. Cool. And then what happens is the body gets called and this gets like copied across. Now what that means is that for the construction of this object, we had to default construct the string first, and then we had to copy assign the new string in. And what that would actually mean behind the scenes is that we probably had to do two mallocs. We had to do the default construction malloc, and then we had to do the copy assignment malloc. That's bad because that was an unnecessary step, whereas if we just did it this way, what would end up happening is that the initializer list would construct it straight into here, and then it would never have to default construct. So there's actually an efficiency performance gain from using the constructor initializer list just because of how it works. So that's something to keep in mind when you're writing code, basically. I ate some chili chips earlier, and they're I can feel them. All right, constructor logic summary. I kind of just described this, so I won't spend a lot of time on it. But basically, for each data member in the declaration order, if it's been used, if it has a used defined initializer, initialize it through the used defined initializer. Else, if it has a built-in type, do nothing. Yeah, sure, initialize it using the default constructor. All right. For each data member in declaration order. I'm sorry, my brain. If it has a use defined initializer. Oh, yeah, sorry, of course. Basically what it's saying here is like, let's say, here's a good example. Standard string J, right? So for all of these, they're going to construct a little bit differently. The first one here will be constructed through the constructor initializer list, as we talked about. The second one here, it'll try and look if it was constructed. It wasn't, so it'll default to it. But because it's a primitive type, it typically will actually just like the construction step is not going to set it to be 0 necessarily here. I'm not sure if that's language defined or compiler defined. I can't remember. It's been a while since we wrote that. Otherwise, in the case of this one, it isn't in the initializer list. It isn't a primitive type, so therefore we need to call the default constructor. I'm really curious now what I would be. I mean, let's just try it out. Maybe it is 0. I didn't write that particular line in the slides, so let me just check. It is 0. I'm not sure if that's by chance, though. It's really hard to tell with some of that stuff. Best to assume that it might not be what you expect it to be. All right, delegating constructors. Oh my God, there's so much to constructors. So a constructor may call another constructor inside the initializer list. Yeah, let's just jump to the code to start here. So ignore the explicit again for a second. Delegating constructors, what it's saying is that inside the initializer list, you can actually, instead of giving it variables like this, you can actually give it another constructor to call. So let's just analyze this class. We've got a class called dummy, and all it has is a string and an int in it, and const int. We construct it with just an int because the string inside of it becomes hello world, and then we store the int that's passed in. And what we're saying here is that this is our kind of general constructor that expects an int. But when we define our default constructor, which just looks like a normal constructor, except it has no arguments inside of it, we can actually kind of say, what I actually want you to do is just call another constructor here where I pass a 5 into it. So this is like a shorthand way of creating an empty or 0 constructor that simply goes and creates a version of it where 5 is the default number. So very powerful stuff because it means that you don't have to go and write a whole separate one. Because if you didn't kind of do that, you know what I mean? You'd actually have to be like, well, I got to copy and paste that, and then I got to do this one here. Like this would be the alternative. You have to do something like this. And that's just going to repeat a lot of code, right? So rather than do this, we can actually take advantage of what we've already written here, and we can simply do that. Maybe that would look like that to some programmers. Now, that one's called constructor delegate. Yeah, now let's see what happens when we do this. Swap them around. Works fine. So some of these kind of rules and understandings can be difficult to get your head around. I still encourage you just to try stuff. So if you ever like, oh, does the order matter? Just go try it. And you kind of know that because if you think about how functions work and stuff, you can sort of define functions in different orders if you need to in a class that's kind of similar to other languages as well. So that's a delegating constructor. Yeah, and I think it is important to note that anything inside of here is called after the delegating constructor. So all of that is, subsequent, basically. Cool. You just quickly check what we got. Okay, cool. So destructors. Destructors are called when the object goes out of scope. That makes sense. You create objects on the stack. At some point, those stack objects go out of scope. They're very useful for managing complex things. We talk about that again with smart pointers. But right now, this is what a destructor looks like. This is a declaration of one. This is a definition of one. And what I've done here is I've actually started to drip feed you the idea of multiple files. Because sometimes when we define classes, what we actually do is, let me just pull this. Oh God, that went to the wrong spot. Oop. Sometimes what we can do if we want to is actually write these across two files, which is a great way to introduce class scope for you too. Because this here is my class definition, right? It defines, I've got a class called my class and I've got a destructor there, but there's no destructed definition here. Now I could go and define it here if I want to. I could literally just put destructed there if I really needed to. However, what can be quite common is that instead in a separate file, or frankly it could even be beneath it, is that I go and define the destructor. Now I can't just write my class like this. I can't do that because my class doesn't mean anything, right? If I kind of had this here, this is just a function name and it's like, well, yeah, but who do you belong to? So we need to scope it properly. Similar to namespaces, but my class is not a namespace. It is a class. Namespaces and classes, their way of scoping things, their ways of scoping things. So that's how we would do that, and we could go and define that, separately in another file if we wanted to. Typically, you don't really do a lot with destructors, mostly because there isn't really a lot to do in destructors a lot of the time, except for clear managed memory and things like that. And we, there are some examples with assignment 2, and we do talk about smart pointers. So yeah, to answer that question, we do teach smart pointers in the course. So we will talk about them more later. For now, there isn't really much you need to do with them. C++ does have the this pointer. It's not an actual, not sure if it's an actual pointer. I can't remember if it's an actual pointer or it's like an abstract pointer. But on the left is the example we were looking at before. On the right is another example where inside the constructor and inside the method, we use this dash, side bracket, arrow, whatever you want to call it, to refer to the actual class itself. Because this is meant to be a pointer, it's meant to be a pointer to the object that you currently have in scope. Some people choose to use this to be more explicit about, what that variable is. The way that we do things in the course is, again, we have an underscore suffix rather than the this, just because we can kind of tell at a glance here that the I underscore and stuff is a class variable, right? So this would be a good alternative if you didn't follow that kind of underscore suffix approach. Tim says, can you actually call a destructor? I don't know. Let's try. What do we got here? Destructor. Let me see if we've got a better piece of code. My class. Standard C out. Destructed. Well, let's first just compile that. Where's the constructor init? Make constructor init. Cool. And then run constructor init. Yep, destructor works. Let me try and explicitly invoke it and see what happens. My class. No matching constructor. Doesn't look like it. I could be not knowing how to do it, but generally, no, you don't call a destructor. I mean, that was going to be my answer, but I wasn't 100% sure. It wouldn't really work anyway. Oh, sorry, of course, that's so stupid. I wrote it wrong. Type my class does not provide a call operator. It is not trying to destruct it here. It is trying to invoke a particular operator that we haven't defined, which we'll talk about more in week 4. But my point I want to make here is that would be weird, because then in theory you could kind of do this here, and then like what even does that line mean if that's now out of scope? So I'm pretty sure you can't, because it wouldn't make sense anyway. Yeah, I don't think you can. It would be hella, even if you could, it'd be a horrible idea. So that's my best answer there. All right. Class scope, incomplete types, a few other things. So when it comes to class scope, anything declared inside the class needs to be accessed through the scope of the class. We kind of referred to this earlier, but here's a more fleshed out example. On the left here, what you see is I've actually got a .h file. Now, typically what you'll do is you go and define the class in the .h file like this, but then you might only declare the functions. You basically do the interface, the API, the prototypes, whatever you want. These aren't any function definitions here, and it doesn't include any, well, actually it does need to include some member methods and stuff. So it's not quite a API. That might have been me speaking a little bit out of place, but you can defer the definitions of the functions, including constructors and destructors, simply by going and writing them in another file over here, which then includes, you know, you include the scope file, you know, you include the .h file, and then you go and explicitly define them. And in this case, you'll see that every single name we have to put the foo : in front of. That's so it's correctly scoped, because without that, it has no idea what you're referring to. Because when you hash include this, the compiler now understands that foo is a class. So by scoping all of these with foo, it knows exactly what you are trying to do, which is very cool. Very, very easy to use. We also will try and, you know, another reason to put the definitions in a separate file is because, you know, if you're compiling 100 files that, you know, use this particular foo class, if you don't go and, if you went and put tons of stuff in the .h, that means that all the code in the .h is going to get copied and pasted into all the files that are importing it. Whereas if you have it in a separate CPP file, it only gets compiled once and then it gets all linked up at the end. That doesn't slow down the program, but it will slow down compilation if you try and include too much in the .h file. Now, here is a sample piece of code. In this case, we've just put everything in the same file. I've got a person class, it's got a name and an age. I've got a getAge, a getName, and I've got a person constructor that simply takes in a name and an age, name by reference since it's a string. Now the constructor here, it doesn't use the constructor initializer list. It does go and create this explicitly. That does mean there's going to be a performance hit for name, because you're going to have to, you know, default construct it, then reassign it. And then we go and define our two getters, which simply return the private fields. And then, you know, we create an object of that class type, just like you'd expect. And then we simply print out something from that, you know, class type as well. Really easy. So, you know, classes aren't too scary. I think, like, if you remember your object-oriented learnings, I think they're pretty digestible. Okay, incomplete types. This one can confuse people. An incomplete type is, you'll kind of remember this maybe from C. This piece of code here doesn't work. Imagine this says class for a second. Just literally think of struct and class are the same word. So imagine this says class. If you go create a class called node, it cannot have a property called node in it. It just isn't allowed. And that's because at this point on line 3 and 4, node hasn't been defined yet, so therefore you can't use it as a type because the type is yet to be defined, right? It's like a chicken and egg problem. You know, this makes no sense. The only times that using a type that's yet to be defined works and is valid is when you're using pointers or references, right? Because a pointer and a reference doesn't really need to understand the type in full. It just needs to know the name exists. And that makes sense if you think about it, because a node in this case, if you're going to put a node in a node, you need to know how big the node is to know how much memory to allocate on the stack. Whereas if you're using a pointer or a reference, the amount of memory is the same. It's going to be 8 bytes on a 64-bit machine, right? And therefore, you don't need to know how big it is because it's just irrelevant, frankly. So you can't do incomplete types. Those kinds of ideas still carry forward from C. There's not really a reason you'd have to do that, but that's another example of where, something like a pointer could be super useful. We'll kind of uncover little bits like that along the way, but again, I wouldn't worry too much about that. Now, you heard me before reference structs, and I was like, classes and structs are the same thing. the term class and the term struct in C++ are almost exactly the same thing. The main differences are that all members of a struct are public by default and all members of a class are private by default. Now, this also makes some sense because if you think about a struct from, C++, your C days, a struct in C, whenever you have the methods in it, well, not methods, sorry, properties, right? You've got struct student, and then, inside of that, you've got char, star, name, and then you've got int age, like this. In this case, right, you can naturally say student dot, or, student name or student dot age. Makes sense. So the properties or the fields of the struct, are public by default, whereas a class, because, it comes from OO land, classes in general don't like to make fields public. They like to be private. Besides that, they're identical. In the course, there's no real reason to use struct for anything. Use class for everything, but again, you will see it used around, and all it does mean is, what is the public-private visibility of particular member fields. Just quickly checking ahead. Okay. Right. So next, we have the explicit keyword. I kind of glossed over this earlier. If a constructor for a class has one parameter, the compiler will create an implicit type conversion from the parameter to the class. That's a bit of a strange description. This is an idiosyncrasy, I guess, of C++. I think the code on the left explains it pretty well, so we'll go and pull it up. I just realized that the reason you can't see my terminal is because I shrunk my dock. Let me just quickly change that. How did I change my dock? Dock, desktop and dock. Yeah. Oops. Is that a little better? I'm trying to watch the recording. Oh my god, I'm so slow on the recording. Damn it. Just make it a little bigger. Let me see how it looks. Nope, still too small. Oh, I don't know. I don't know what I'm doing. Just ignore me. I'm messing about. It's not really helping. So what we'll see with the explicit one here is that these two examples make sense, right? If this one was auto, it's kind of the same thing. You've got your standard case, you always use auto case. They both achieve the same result. You create an age thing, an age object. It uses braces. There's no initializer list, so what it does is it simply calls A1 with one parameter, and it goes and invokes it. Now, some weird exceptions are, if you do this and you say age A3 equals 20, what you end up doing is the compiler will say, you're trying to assign an integer to an object. Now, that doesn't make sense because they're different types. However, I'm going to go have a look at the object and see if the object has a one parameter constructor that takes in the type on the right-hand side, which is an int. Oh my god, it does. And what it will do is it will implicit because you didn't ask for it explicitly, it will implicitly invoke the constructor for that element, and it will work validly, totally fine without an issue, and the program will run successfully. However, if you put an explicit out the front of this, it will not work. So if I just take this code for a sec, and I go and say make explicit 1. There we go. 3.1, explicit 1, I get 20. Sure, I go and put an explicit out the front there. Straight away, compilation error. No viable conversion from int to age. Makes sense. There's no conversion because we didn't allow a conversion, because the explicit there stops any implicit conversion being possible. That's what the keyword does. I would probably generally recommend having that on. I can't see why people would ever want their code to be more obscure, than otherwise, really. So yeah, we've got another example here. I can quickly look at that. This one, explicit, it's simply showing you that if you tried to say int vec equals size, it wouldn't work. It's the same example as the other one. I don't need to kind of step you through it line by line, but that's what the explicit keyword does. I generally recommend writing it in front of all of your functions, unless you really, for some reason, don't want it to work. Okay, now, a fun one, const members. This can get confusing, and it's quite important for assignment 2. Member functions, or methods, as some of you call it, depending on the courses you've done, are by default only callable by non-const objects. Or const member functions. Member functions are by default only callable by non-const objects. Yes. Yes, that makes sense. Let me just jump back a sec. Tim says, is that the main reason of explicit though to enforce style readability? I don't know. That's all that I know about, at least. You're essentially just prohibiting a particular usage of your function. I just don't think the implicit constructor is very good programming style. This is weird. It doesn't make sense. So yeah, that's my take on it, at least. I'm sure there might be some other interesting ones. Again, I think I might jump straight to the code with this. Const is a funny thing when it comes to classes. I've got a person class here. It's got some public stuff in it, right? You saw this before. Name, get name, set name, fairly standard kind of, classes 101 type here. Then I've got a main function. I create, an object P1, like that. Cool, called Hayden. And then I set the name to be Chris, and then I print out the name, right? Cool. However, what we haven't talked about is in C++, you can go and create a const int or a const string. You can also create a const object. So in this case, I can say person const P2 Hayden. However, once I create a const version of the object, some weird things will happen if I try and do stuff with it. If I get rid of these two lines here, right? Const members. Yep, see straight away. This argument to member function set name has type const person, but the function is not marked const. So what this is saying is that if you have a const object, it will only be happy calling a const qualified member function. And what that means here is, let's just get rid of this set name for a second. Now, let's have a look at this one. Oops, wrong one. Const members. This doesn't compile, but that's kind of confusing because get name doesn't modify anything. I'm not changing anything. So why is the compiler not working? It is const, the object's const, I'm not changing anything. And that's because what the compiler will do is it will look for this version of the function. It'll look for the version with the const after the parentheses. And if it finds that, it will invoke that particular one. So this code works now. When this get name is called for P1, it is called, well, yeah, maybe. I'm pretty sure it's calling this version here. However, this one here on P2, it is calling this version here, this get name. When I do set name on the const object, it is looking for a const version of set name too, right? So if I do that, the compiler, the code will try and compile, but I'll still run into problems. And the reason I'm running into problems this time is because now that the function is marked as const, it is not allowing me to mutate anything inside of it, right? Because a const member function can't mutate anything. What this means, it's very intuitive once you get used to it, but it's basically just saying that we don't need to make a const constructor. No. This has nothing to do with constructors or destructors. It's just member functions. What this means in practice is that wherever possible, you should always mark your functions as const. The reason for that is because if you have only a const function for getName, it is happy to be called by both const and non-const functions, right? Objects. So if you have a const function, a const object and a non-const object can both call it. But if you have a non-const function, only non-const objects can call it. That's how the example started, right? And this kind of self-corrects, because what this means is because you can't mark this function as const because you're mutating something, it means that it's literally just not possible to call setName on a const object. So that just isn't possible at all. Why is const added after getName? Bill says, because when I add const to it, it says this version of the function, this function can now be called by const objects of a person, or P2 in this case. Without this const here, P2 can't call getName. And because you always want your class to work for const and non-const objects, right? You want it to work for normal persons and const persons, then you mark as many functions as you can as const. And you can mark every function as const. That doesn't modify anything, basically. Tim says, if you remove the non-const getName from the class, well, yeah, okay, already answered that one, obviously, which is good. Bill says, I mean, why is it not auto-const? I like that one. So the question is like, why is it not auto-const? I don't know why it's, sorry, wrong way. I don't know exactly why it's like not that. I mean, if I maybe break it up a different way and I move this back over here, right? The reason I think the const is at the end is simply because if we had it there, the compiler and the language definition will get too tricky trying to figure out what you're trying to do there. So the way they just decided, because all language decisions are largely arbitrary, is they decided to put it at the end to help separate it from the actual return type there on the left. So MKH says, so is it class const var name is only used for call all const functions? Yes. If you have an object person, which is of type class person, sorry, if you have an object P2, P2 is the object of type person, or more specifically, a const person class type. This P2, because it was marked as a const class, can now only call functions with this const after the parentheses. That's the rules around const and members, basically. Yes, and correct, you would normally do this. You would normally say auto equals person. This is a much better way. Auto const P2 equals person, like that. Yes, that is how you would do it. All right, last couple of things. Looks like static members. Static members belong to a class as opposed to a particular object. This is all not new knowledge because you should know this from other OO courses. Basically, static members aren't stored with the object because, you know, if you have a one class definition for a person and 100 person objects, there is only one static field or one static member. Therefore, it's not stored with the class, with the object. It's stored with the class. The examples of static we have here are Yep. So we got a user here. And what we, oh, sorry, that's before and after, isn't it? Yep. So in this particular case, I've got a user, I construct it, it's just storing a name, and then I simply have a function, a Boolean function valid name that returns true or false depending on whether the name length is under 20, right? Now, what you'll notice here, this is a bit of a silly function, but this function doesn't actually rely on, not my favorite example. This function doesn't rely on anything like to do with the object itself, right? Like, so when I call this here, I say, you know, I create a string called n, which is Santa Claus. I create a user called u. which passes in that string. And then I simply say, hey, if u.valid name of n, where n is the Santa Claus string, do something. But because this particular, this is a member function of an object, but it doesn't use any object fields, I can make it static, and I can make it static simply by putting static out the front. I'm not going to cover the staticness thing again because it is meant to be prerequisite knowledge, but the point I'm getting at is that from a syntax perspective, you're simply adding static to the front of the function declaration definition. And when you invoke it, because you're invoking it from the class and not an object now, instead of, doing it like object dot something, it's actually just like class : something, just like namespaces and std and things like that. So that's what to do with static. But there's not really much static in the course. You won't come across it a great deal. All right, so last part of classes today is defaults. Just a bit more academic theory. So we have the synthesized default constructor. So in a class, you can create a class and that class can have no constructor. You can create a class like this one, A. Class A, it simply has a member field A underscore. If you create a class called A with just a field and no constructor, the compiler will generate a synthesized default constructor. Synthesize means that it kind of creates it. And it only happens again if your class declares no constructors. And what it does is for each private member, it calls the initializer for it. Otherwise, it calls the default constructor, right? So same kind of rules we've been seeing before and so forth. What that means is if you've got a class here called B that does have a default constructor and A that doesn't, let's now look at a main function. If I say int I underscore, what it will do, and I think this is kind of where the distinction is quite interesting. In this particular case, if I say int I underscore, because I give it a little brace and a 0, it forces it to obviously define that particular variable to be 0. If I just say int j like that, declared, it gives me that piece of memory, but it doesn't touch it. That's the one where I can't be sure it's 0. This one is always 0 after definition because, I told it to be 0. Whereas this one could be anything. And if I call a like this, just double checking, this right here will not create a default constructor because I'm not actually trying to define that object at this point. I'm just declaring it. It's very confusing stuff. Again, mostly academic. I wouldn't get caught up too much on some of these examples. I'm not, again, a massive fan of it. I'd mostly just say that you just need to understand that you can, if you create a class without a constructor will be created for you, a default constructor with, no parameters being passed in. Oh, this one's kind of fun. The compiler will also create destructors for you. It'll create constructors, destructors. It'll create a bunch of stuff that we don't talk about, I think, till week 5. Just because you don't write it, the compiler still needs it. Like if you have a piece of code like this, class A, and all it's got inside of it's int A underscore, the compiler will allow code like this to work. Again, we'll talk wrong. That won't work. Like this to work, where you can create A and then copy A to B without any more definitions, because it needs those functions to exist. It does go and do that. However, there's a really interesting thing you can do in C++ where is it in this example? Oh yeah, sorry, I've commented it out because it won't compile otherwise. But if we have a look at this one, what you can actually do in C++ is that you can tell C++ to not create a function for you. So if we look at this class called intvec, this is a constructor. It simply takes in a a vector, right? So it's literally this silly little class that just has a vector of ints in it. And when you call it, you tell it how many zeros you want that vector to have. So in this case, I say intvec a or auto intvec equals a, just to be really consistent with our best practices. I'll go clean that lecture code up. Sorry about that. I think we screwed something up. So that'll work, right? Because we've got that. It'll create a, an invec object that has a vector inside of it. That vector has 4 zeros because we're delegating constructing to the vector using a few ideas here. But then if I have this line here and I say, you know what, auto, sorry guys, that's bad code. That didn't make any sense. Yep. Here, when I say b equals intvec a, it will try and copy construct it. It will try and say, well, you know what, a's of invec. So I'm just going to copy that and it will create a whole copy constructor for you. However, what you can do is you can come along and actually mark it as deleted. And if you mark it as deleted, it's like an instruction to the compiler to say, I don't want you to synthesize this. Like, please just like, don't. Just like let it die. So if I get rid of that, if I put that there and I try and run this now, I'll get a compile error that says call to deleted constructor of invec. This again has some interesting use cases that we will talk about in week 5 when we talk about smart pointers, because you might be thinking now, why would I want there to be less functionality? There are some interesting cases where you don't want things to be able to be copy constructed, and you can mark more things than that as default or deleted. But again, we will get to that later. That brings us to the end of today for 3.1. Thank you for tuning in. For those who've joined us online, good, strong turnout. Appreciate your understanding as we had to move this one around a little bit. Yes, that's all. Hope you enjoyed learning about classes.